EC 201, lecture 43. Yesterday we were looking at the closed loop properties of a feedback system where the forward amplifier is a 3-pole design. So A of S was of the form A naught divided by 1 plus S by omega P the whole cube, and we were trying to find where the roots of the closed loop system lie, and we said that the denominator polynomial of the closed loop system can be written in the form D of S is S by omega P the whole cube plus 3 S by omega P whole square plus 3 times S by omega P plus 1 plus A naught F. Okay. So the poles of the system are the roots of D of S. You can treat S by omega P as the variables instead, and finding the poles reduces to finding the roots of a polynomial S cube plus 3S square plus 3S plus 1 plus A naught F. And all of you readily saw that this can be written as S plus 1 the whole cube equals minus A naught F, which means that S must be equal to minus 1 plus minus A naught F the whole power 1/3. As an example, we said, let's see, choose A naught F to be 8, in which case what happens? S becomes minus 1 plus the cube root of minus 8, and minus 8 has got 3 cube roots. All of them lie on a circle of radius 2. One root is here. Where will the other 2 roots be? Here. And this angle will be 60 degrees. The radius of the circle is 2. So the roots of the equation are minus 1 plus the 3 roots of minus 8, which are minus 2, 1 plus minus j plus root 3, correct. The 3 roots are minus 3, what else? Plus or minus j root 3. The poles of the closed loop system are at minus 3 omega P and plus minus j root 3 times omega P. As we expect, the poles appear in complex conjugate pairs, and definitely plus minus j root 3 times omega P are complex and conjugate. Is the system stable or the roots are on the j omega axis, so technically it's stable, but you'd never want to have an amplifier like that, because the impulse response of such an amplifier will have a sinusoid with a frequency of root 3 omega P, and that will continue on forever. The conclusion is that even if A naught F is as small as 8, the system is unstable. What do you think happens if I increase A naught F further? So S plus 1 the whole cube, A naught F increases further. We know that we're trying to find the roots of S cube plus 3S square plus 3S plus 1 must be equal to minus A naught F. So what are the sum of the roots? It is minus 3. And is that dependent on A naught F or is it not dependent on A naught F? The sum of the roots is always minus 3 and is independent of A naught F. When A naught F is 0, for example, where are the roots? Minus 1 and minus 1. We have 3 roots. As you go on increasing A naught F, what happens? For A naught F is equal to 8, what did we see? Plus minus J root 3, and we saw another root at minus 3. What do you think would have happened as the gain was changed if I plotted the roots? I changed the A naught F by a small amount, recalculate the roots and plot it. I will get some kind of curve. Correct? What do you think I would have got if the A naught F, this step here corresponds to A naught F is equal to 0. This shows the position of the 3 roots of the polynomial as A naught F when A naught F is equal to 8. So between 0 and 8, what do you think would have happened? It would have done probably something like this. And it makes, this makes sense because as A naught F is increasing, one root is the cube root of A naught F, minus 1 plus the cube root of real cube root of A naught F. That moves to the left, but the sum of the roots must be minus 3. So these two complex roots must move to the right. You understand? So if I go on increasing A naught F beyond 8, what do you think will happen? The poles will get into the right half plane and the value A naught F is equal to 8 defines the limit of stability. You understand? So what is the whole idea in starting off with the third order system? The whole idea in trying to have a third order forward amplifier was to be able to have as large an A naught as possible. Initially had grand plans of starting off with A naught is 10 power 4, 10 power 6. But the moment you have 3 poles and you put some F in feedback, the maximum A naught F that is possible, we would ideally like to have A naught F to be equal to infinity. But even when A naught F exceeds a small number like 8, the closed loop system becomes unstable. You understand? One thing you can say is, okay, let's go and try fourth order. We saw that first order was nice and clean, second order was kind of just pass, E grade. The third order is definitely U. Fourth order, I think there's no point in even talking about it. Those who are really skeptical can go and do the maths. You will find that the limit for the gain will be even smaller than 8. So the question to ask is there some way in which I can have a large A naught F and the system be stable? This is a natural question, correct? Let's see if our prior experience can help us figure out a solution to the problem. So the question is it possible to have a large A0F and closed loop stability? The points I wish to point out from our previous discussion are the following. One, a first order system is unconditionally when I say first order system, I mean the power amplifier is first order, is unconditionally stable for all A0F. But unfortunately, the first order system cannot have a large A0F because of fundamental device limitations. You cannot realize a large A0F using a single stage. However, the third order system can realize a large A0F, but the moment you close the loop, it starts oscillating. So the question is there some way of combining the merits of both situations? One solution is the powered amplifier was of this form, the A0 by 1 plus S by omega 1, the whole cube. So the solution is, say, what if I cascaded this with an amplifier which had 1 plus S by omega 1 the whole square. Can I realize 1 plus S by omega 1 the whole square? Is it possible to just realize a pure zero without a pole? One thing you can see is that the gain of this becomes infinite at infinite frequencies. I should tell you something is fishy. Anyway, it turns out that you cannot realize a zero without a pole. So the only thing you can do is, for example, if you want to do this, you must be able to do something like this. The basic idea is to try and see if you can make it a first order system. So clearly, if you you can try and cancel two of these guys, perhaps you can, but you can see that the order of the system has to increase. You understand? This is the order of this system is now fifth order system. The direction which you are going is right. You know that the first order system is unconditionally stable. So if you somehow make the third order power amplifier look like a first order system, then it should work. Correct? The basic idea is, let's try and make third order powered amplifier look like a first order. So how do you think I can accomplish this? The third order system we had originally was A0 times 1 plus S by omega P the whole cube. Now, if instead of having this, if I put in cascade with the system a first order system with a pole at omega d, where omega d is, this is the modified system, will look like a first order system if omega d is much smaller than omega. Does it make sense? To look at it in pictures, if I plot log omega versus the magnitude response is also, magnitude is on the log scale, the frequency is also on the log scale. If I plot a system of the form A naught divided by 1 plus S by omega d, at very low frequencies, what do you think the magnitude response will be? I mean, first of all, why would I want to plot on the log scale? I could have easily plotted on the linear scale, isn't it? We are dealing here with a large range of numbers. Omega d is much smaller than omega 1 and this A is a very large number hopefully. So, since we are dealing with large numbers, the picture will look better if I draw it on a log scale. So, if I plot log of magnitude of A of S, A of, for very low frequencies, this is log A naught. For omega becoming much larger than omega d, if I plot on a log scale, how does it look like? It goes down as a straight line, and what is the slope? The slope is -1. For large omega, this goes as A naught times omega d divided by omega. So when I plot log of this, I get something which falls off with a slope of -1. So for large omega, if I plot on the log scale, this should be a slope like this. This is what a first order system would look like. On the same plot, if I plotted the third order system, how does it look like? Okay, instead of plotting A naught, I could also plot A naught F because that's what we're typically interested in. So it's A naught F, so this will be A naught F. A naught F by 1 plus S by omega d. So if I wanted to now plot A naught F by 1 plus S by omega p the whole cube, which is the original system that we had, how will it look like? Let's assume that omega p was somewhere here. It's much larger than omega d. Please note that this is a log scale. So it really means that omega p is very large compared to omega d. For very low values of omega, this would be a constant. It will be log A naught F. For frequencies much larger than omega p, how will the plot look like? It will look like a straight line with a slope of -3. If this is 0, that basically means that a log of the magnitude is 0, this 0 line here corresponds to gain being equal to 1. So if I now cascade the original system with 1 over 1 plus S by omega d, since these are all log plots, it is simply addition of 1 by, not these two curves. I have already accounted for A naught F by 1 plus S by omega d. So how will the combined plot look like? For frequencies much smaller than omega p, it will simply follow A naught F divided by 1 plus S by omega d. So the combined log plot will look something like this. supposed to be on the same line. Okay, so the combined plot will look like this. It will follow the first order plot up to about omega p. Beyond omega p, what will happen? For frequencies much larger than omega p, it will fall off as with a slope of -4. So it will do something like this. Alright? So this corresponds to the log magnitude plot of this character. So in this region where the gain A of S times F is greater than 1, please note that again that this is a log plot. I mean, in this frequency range, the value of the gain is it's greater than 1. So what do we see? We see that in this frequency range where the value of loop gain, which is A of S times F, in this frequency range it is always greater than 1, and in that range the frequency response of this system is completely indistinguishable from that of a first order system. Is that clear? Alright, so why am I so harping in this region where A naught F is greater than 1? What is so special about this naught F being greater than 1? If we said, what are we trying to do basically here? We are trying to make this third order system look like a first order system. Alright? And if you want to make it look like a first order system, what will you do? I will try and match its frequency response over a certain range of frequencies. And that range, okay, at least in this picture, definitely in that range where the gain A naught F is greater than 1, the two of them seem to be matched. And I claim that anything that happens in the frequency range where A naught F is smaller than 1 doesn't matter. I mean, why does that statement make any sense? At frequencies here where A naught F is very small anyway, I mean the amplifier is completely dead and feedback can't be doing anything to hurt. You understand? So at frequencies where the forward amplifier gain is so small, hardly any output at all. The negative feedback is helping you only when A of S times F is much larger than 1, and the critical point where things begin to start failing is around about the region where A of S times F, which is the loop gain, is around about 1. If the frequency is so high that the gain of the forward amplifier becomes much smaller than 1, then never get the closed loop gain to be equal to 1 over F anyway. Alright? So if you want this fourth order system to look like a first order system, it's only important to make it look like the first order system in a frequency range where feedback action is actually occurring, and that only occurs when the magnitude of the loop gain is larger than 1. Do you understand? If for example omega p was somewhere here, so that this is what it did. In this region, the fourth order system still looks like a first order system. Okay. But things start to go wrong here. Understand? And you can't be sure of unconditional stability anymore. Does it make sense? So it's like this. I mean, obviously nothing comes for free, because earlier the loop gain we had in this region here, the loop gain we had over this frequency range was much higher than what we have now. Correct? So all we have done is we have deliberately killed the bandwidth of the amplifier and lost So earlier the loop gain would be very flat up to a very large frequency and then fall off very rapidly. What we have done is now make it approximate a first order system so that we make the closed loop system stable. But what we have lost in the process is the fact that the loop gain, which was much higher over this frequency range before, is now much lesser. The loop gain function is now this, the magenta curve. Does it make sense? So let's make some calculations and indeed confirm that this is the case. An example. The original system was A naught F divided by 1 plus S by omega P the whole cube, and we know that maximum A naught F for stability is 8 for this system. Now let's try and introduce another pole at a frequency 1 plus say omega P by 1000. This is the factor 1 plus S by omega D. And let's see, what the maximum A naught F is, which you can now tolerate before the system becomes unstable. Hopefully we should definitely try to improve one on 8, isn't it? So the closed loop transfer function is nothing but 1 over F times this function loop gain divided by 1 plus loop gain, and the loop gain is basically A of S times F. If A naught F went on increasing, first the poles will all be in the left half plane, then all these poles will split and they will go to the right half plane. So at some point during this journey they will sit on the j omega axis. That gives you the critical amount of A naught F beyond which the system becomes unstable. If we are interested in finding that critical A naught F, so at the limit of A naught F for stability, the poles of the function of the denominator are on the j omega axis, which means that what happens to the denominator evaluated on the j omega axis? If the poles of a network are on the j omega axis, and if I evaluate h of j omega at those poles, what will happen to the network function? The denominator polynomial will go to 0. Is that clear? So one could in fact write out the fourth order polynomial and find the roots, and find where the roots will obviously be a function of A naught F. You can find when the roots sit on the j omega axis. An alternate way of doing the same thing is to find when the loop gain function becomes equal to -1. Does it make sense? To be a little more precise, the loop gain function evaluated on the j omega axis becomes equal to -1. If this is satisfied at a certain omega x, then it basically means that the denominator polynomial, which is 1 plus loop gain of j omega x, becomes 0, which basically means that poles are on the j omega axis. This is just another way of finding the limit on A naught F before weird things start happening. Is that clear? As I said again, there is nothing at all wrong with writing out the complete equation in the S domain. You will get a polynomial, fourth order polynomial in this case in S, and then find the roots. The roots will be a function of A naught F. You can find what A naught F, the roots will just jump into the right half S plane, and you're all set. And this is a useful method, so I will try and illustrate this with an example. We want to find 1 plus j omega x divided by omega p the whole cube times one plus j omega x times 1000 by omega p must be the poles of the system are on the j omega axis. This value must reduce to minus 1. Correct? So there is clearly a magnitude criterion and a phase criterion. What is the phase response telling you? So the phase of the loop gain must be equal to 180 degrees at omega equal to omega x. So can you now help me figure out what this must be? Minus 3 tan inverse omega x by omega p minus tan inverse 1000 omega x by omega p must be equal to, the math is alright, we will get to it. But intuition wise, where do you think the omega x should be? Is it going to be less than omega p by 1000? One thing to observe is that omega x must be greater than omega p by 1000. Because if it's less than omega p by 1000, this itself is 45 degrees, this will be 1000 times smaller approximately. So the three phases will never add up to 180 degrees. Okay, that's fine. So the question is, will it be greater than omega p? Omega x happen to be greater than omega p. Even if this omega x is equal to omega p, we see that each of these contributes 45 degrees. 3 times 45 degrees is 135, and then if this contributes 45, what will this term contribute? Almost 90. Okay, so that should give you 90 plus 135, which is 225. So where do you think the omega x will lie? The omega x must lie between less than omega p. Number will lie somewhere between omega p by 1000 and omega p. Second dirty way of finding the solution is to notice that if omega x is much larger than omega p by 1000, then 1 by 1 plus s by omega p times 1000 contributes minus 90 degrees. Is that clear? Which means that 1 by 1 plus j omega x by omega p the whole cube contributes the sum total of all these angles is 180 degrees, guys. Okay, this guy contributes 90, so the other three must contribute 90 and minus 90 degrees, which means that 1 plus j omega x by omega p must contribute minus 30 degrees. Okay, which means omega x is omega p by root 3. Definitely you can see that omega x is p divided by root 3. To make this equation come true, which means that the phase condition is satisfied when omega x is approximately omega p by root 3, which means what happens to the magnitude condition? This is 1 plus a by root 3 whole cube times 1 plus 1000 by root 3 j must be equal to 1. But this is approximately 1 plus 1/3 the square root whole cube times 1 plus 1000 by root. This must be equal to 1. So the A naught F that you can tolerate before the system becomes unstable is 1000 by root 3 times approximately square root of 4 by 3 is about 1.15 or so. 1.15 whole cube is about 1.5. 860. Does it make sense?